Hello students, welcome to this video. This video is going to go over the computer assignment number 3, which is all about confidence intervals and hypothesis testing for chapters 7 and 8. So here's our instructions, and it says to go into the Excel file, which is over here, and let's bring that over there. So this is the Excel file you should be working on. The values in orange are set to change every time you press a button. So the first thing you need to do is go highlight all of the orange values, copy, and use this paste values 1, 2, 3. Or you can go into paste special, but this one's nice and quick right there. And now the values will not change. So it's a series of using Excel functions and formulas to develop a confidence interval and to run the hypothesis test. And in doing so, you'll be able to see the size, the power of the different sample sizes. So the first thing we want to do is we have 6 different samples, and they look like they're the same sizes, but we have quite a few rows hidden in between. So what we want to do is develop or use the count function, equals count bracket, highlight all of your data, and there's actually 10 values in there. Some of them are hidden. The average function, bracket, once again, highlight your data. Standard deviation function is listed on the instruction sheet. It's stdev, bracket, highlight all the data. Max and min as well, basically showing the largest value in the sample. Now there are a few values hidden in there, so we won't see all of them. But basically in the sample of 10, our largest value is 119, smallest value is 74, has an average of 92.4, standard deviation of 13.517. And if we highlight all of those and drag them over or copy and paste over, there we go. So sample 6 has a sample size of 1,000, and it has an average of 99.5. All of these are slightly less than 100. So once again, because everyone's working with different data in orange here, these values here will all be different. We'll all have the same count, but the average, standard deviation, max, and min will be different values. So we know that if we were to go into our normal t-distribution chart, we could find the actual t alpha value that we need to develop our confidence intervals. And let's do that for the first confidence interval for the t alpha value. The instruction sheet says that we're building a 95% level of confidence. So alpha is 5%. Degrees of freedom would be n minus 1. So the first one would be 10 minus 1, so 9 degrees of freedom. Alpha is 5%, but we divide it by 2 for confidence intervals. So basically our t value is going to be 2.262. When our sample size is 30, we're going to continue down that same row, go down to 29 degrees of freedom, and have this value, 2.045. But because we're in Excel, we don't want to manually enter these values. So we're going to use a function. It's a tinv function. So tinv bracket, and then we're going to enter the chance of error, 5%. Comma, degrees of freedom is going to be the count minus 1. And there is that value that we had just found on the t-distribution chart. If we copy or drag that over, we'll get the t value for 30 degrees or 30 sample size, which we also found on the t-distribution chart. These ones weren't available, but we're confident that these ones are the correct values. The standard error formula is the standard deviation divided by the square root of the sample size. So this is going to be a formula. We're going to go equals, click on the value for standard deviation, divided by, enter the function for square root, SQRT bracket, and click on the value for the sample size, and that is our standard error. Of course, everyone's getting different values here. Everyone will have the same T alpha values, but the standard error is going to be different because everyone has a different standard deviation. So we know as we continue on with this confidence interval, the next part would be to calculate the margin of error. Margin of error is going to be the standard error, the T alpha value, times the standard error. This is the plus minus number. If we look at this, just bring up the formula here, we have calculated this is the standard error, S divided by the square root of n, and all of this is the margin of error. This T value we have, which is based on half of the chance of error with n minus 1 degrees of freedom, that is the T alpha value. So T alpha times the standard error gives us our margin of error. Everyone will also have a different margin of error. Now what we can do with this confidence interval, the confidence interval is basically 92.4 plus and minus 9.670. So what we can do is develop an upper level, which is going to be the average plus the margin of error. And of course the lower level is going to be the average minus the margin of error. And then we can drag this across. So remember, confidence intervals gives us the range at which we are 95% confident that the population mean, which is unknown to us, but we're 95% confident that it's somewhere within the lower and upper level for each of these intervals, or for each of these examples for the sample size. So what we want to enter in step 2e is a really interesting if function. We want to determine if a population value falls within the upper and lower level. So what we're going to enter is an if function, and I really like if functions, but I'm not a big fan of the if. Oops, let's do this again. Let's go if. What we can do is press the FX button, and it'll give us this pop-up window. And it's a logical test. If a value is true, it's going to give us something. If a value is false, it's going to return something as well. But we're going to have an if and function. And it's not one of my favorite functions, but we make it work. So the if and, you type in and in that logical test with a bracket, click on the upper level value, and we want to determine if that is greater than 100, comma, click on the value for the lower level and determine if that's less than 100. Close your bracket. The logical test will be that if it's true, we want it to return saying yes. And if it's false, we want to type in no. So basically what this means is that we are assuming, or we know that the population average is 100. Does the population average of 100 fit within this interval? Interval being 82.7 to 102.1. Yes, it does. So that's why we want yes. If we drag this across, we will see that there is one example here in the data I'm working with. That is no. Basically, the interval 97 to 99.7 does not include 100. So you may have all yeses, or you may have one, maybe even two no's. But basically, if the interval does not include 100, we want it to say or return saying no in this row. Now remember, we are developing 95% level of confidence, which means that there is a 5% chance that the population mean is not going to be within this interval, or that the interval doesn't include that population mean. So when we do this hypothesis test, Step 3, we want to calculate the test statistic. The test statistic is going to be using this formula here. This is formula we've used in hypothesis testing, the sample mean minus the population mean, which is assumed to be true value, divided by the standard error, S, over the square root of n. So we're going to enter this formula. We need some brackets. It's going to be the sample mean, the average, minus 100. So manually type in 100. And we're going to divide it by the standard error, which we already calculated to be as the standard deviation over the square root of the sample size. Some of the values will be negative. We don't like negative values. So what I want you to do at the very beginning of the formula that you've entered, right after the equal sign, is enter ABS with another bracket at the beginning and a bracket at the end. This is a function that will return all negative values as positive. And then we can drag that over or copy and paste that over, and we get test statistics. Some of them are large, some of them are small. We're now going to develop, using another if function, a decision, because we've calculated, the question states that this is a two-tailed test. The claim is that the population equals 100. The population average equals 100. That's why we use 100 in our test statistic. So we have our critical value right up here. These are the critical values, and we're going to compare them to the test statistic. So our decision process will be an if function. If the test statistic is greater than the critical value, we will say reject the null hypotheses. If it's opposite, we will say do not reject the null hypotheses. Our decision is going to be do not reject the null hypotheses. We can drag that across. In this case, for my example here, I have a reject the null hypotheses decision because the test statistic 2.416 is greater than 1.965. The last part we want to do for this first sheet is to calculate or define the p-value. Now we know how to find p-values when we start with a z-value. The process when we start with a t-value is a little different. What we're going to do is use a function. It's the t-dist function, t-dist bracket. Then I'll say click on the value for x. The x value is our test statistic. Degrees of freedom is back up here, sample size minus 1. And then it'll say the number of tails. This is a two-tailed test, so we're going to manually type in 2. And that is our p-value. Drag that across. We get p-values. Now the benefit of the p-value is it tells us the strength of our decision when we reject the null hypotheses. The examples I'm using here, we're not rejecting the null hypotheses. P-value is quite high, whereas in column F, for my example here, I have quite a low p-value. Our decision process to determine when is a p-value really low is using alpha as that threshold. So we also want to develop an if statement for the p-value test. So if the p-value, click on the p-value, is less than alpha, type in 5%, 0.05, we're going to say reject the null hypotheses. And the opposite would be do not reject the null hypotheses. And we get that decision, we copy that over. You'll notice that the decision in 3b and 3d are the same. Just let me highlight this. Those decisions are the same, and that's what we find. And before we move on to the last part, just want to highlight that in this hypothesis testing, which is a two-tailed test as per the instructions, we have made our decision right in this row here based on comparing the test statistic, which we've calculated, to the critical value T alpha back in 2A here, and making that comparison, we have decided not to reject the null hypotheses, which means that the average, we don't want to say that it equals 100, but we can't say that it's different than 100, except for, in my example here, you may have different results. You probably will have different results. But in sample 4, we have enough justification and evidence to state that in sample 4, or sample 5, I should say, there should be 5 there, silly me. Sample 5, the decision was to reject the null hypotheses because the test statistic was bigger than the critical value, as well as the p-value is smaller than the threshold value being 5% alpha. So we are rejecting the null hypotheses. You'll always get the same decision. So make sure that your decision for 3B is the same as your decision in 3D. Okay, let's move on to the last part of this. We're going to go into the frequency tab. And this shows the frequency distribution for the previous samples that we've collected. This should be 5. So this distribution for column B, sample 1, when the sample size was 10, this is the distribution of the values in it, which is only 10 values. So what this is going to show is the power of having a larger sample size. Larger sample size are always better, but it comes at a cost of time and money. So it's much easier to survey smaller, but then we are less confident perhaps in the values we get, and our answers are not as precise. So what we want to do is create histograms. We're going to just focus on groups 1, 2, and 6. So the first thing we want to do is highlight column A and B, not all of the column, just from classes, row 2 down to row 14, and insert column graph. This is a column graph. We want to change it to a histogram. To change it to a histogram, we right-click on one of the columns, go to Format Data Series, and reduce this gap width down to 0%. There is our distribution. Does not look like a normal distribution. And of course, your distribution will look different because these values we have in column B, the frequency for all of the classes are going to be different as well. But for my example, it does not look like a normal distribution. It looks like half of a normal distribution. So we want to do the same thing for group 2 and 6. So when we need to develop a graph for columns that are not joined side by side, we highlight the first column as normal from row 2 down to row 14, press and hold the control button, and then highlight the values in the column that we want. In this case, column C for sample 2. Let go of your control button. Both should be still highlighted there. Go Insert, Column Graph. This one looks a little bit more normal. Doing the same thing, same process. Right-click on one of the columns, Format Data Series, reduce the gap width down to 0%, and there it is. Let's change these over. And the last one will be group number 6. So once again, highlight classes, press and hold control, and then to do the same thing for column G. For sample 6, let go of control, insert, column graph, and right click on one of the columns, format the data series, and gap width down to 0%. This one looks more normal. So the question is, or the benefit of what we're seeing here, is that larger samples appear more normal. And there is, a thought that once your sample size is at least 30, it starts looking more normal. If you wanted to, you could do the same thing for these other columns. Rather relatively easy process, and you'll see that once we get past that 30 mark, sample size of 30, generally it starts to appear more normal. So 30 is a key number in statistics and sampling. Basically, less than 30, we can't assume that follows a normal distribution, so we have to use other distributions, like the t-distribution. Whereas once we get larger sample sizes, it generally does appear more normal. So in the shaded blue cells, comment on the differences between the three graphs in terms of the shape. Is one, the larger sample size is generally going to appear more normal, smaller sample size or not. Now you may have different shapes, and it'll be interesting to see what kind of comments you have based on the distribution shapes of the three graphs that you're asked to do for step 4. Okay, so this lab or this computer assignment basically showing you the power of the sample size and how to develop confidence intervals and hypothesis testing using some of the Excel functions and tools. And that is it.